going back to the definition of rate of change. To say that omega is a rate of change of theta with respect to t is to say that omega equals change in theta divided by change in t. Now, many of you have already kind of skipped this step to the point where you understand it's a slope of a certain graph because the rise and the run and so forth. You have to go back to the definition and make sure you really understand how that's connected. What you're saying is true, but it's a little bit insecure if you don't know the exact words of the definition of a rate of change. Okay, so in the words, it'd be change in theta divided by change in t, and that would be the average rate of change of omega with respect to t. And that would be delta theta divided by delta t. There's also an instantaneous rate of change that we've talked about. I'm not going to talk about that right now because we don't need it to solve this problem. Okay? So that's what omega means. And then what does alpha mean? It's the rate of change of omega with respect to t. So that's change in omega divided by change in t. So that's delta omega over delta t. Now this is extraordinarily important because we're going to be trying to calculate the change in omega and the change in theta, because omega tells you how fast the thing is falling and theta tells you where it is. So at every step we need to know where it is and how fast it's going so we can predict a millisecond later where it's going to be and how fast it's going to be moving. Okay? That's very critical. Now how would we know this is what we need to do, other than the fact that we've done this with some simpler situations where we don't have two different rates, we've just got one rate, as we do in many problems. Well, let's see what we have to do. Okay, we're starting. We know that theta is 1.2. And this really means 1.2 radians, and it's kind of helpful to maybe write that down to keep reminding ourselves of what we're doing. We can even picture 1.2 radians. 1.57 radians, actually pi over 2, to three significant figures, that's 1.57, is a right angle. So that means a domino would be straight up at 1.57 radians. It would be flat at 0 radians. At 1.2 radians, it would be something like this. And you might think about that. Okay, if theta is 1.2 radians, then and omega is 0. And I'm not sure I want to let omega equal 0. In the problem that we've been working on, omega was 0.1 radians. So I'm going to say omega is 0.1 because that allows me to avoid something that I just realized I want to avoid. Just a little extra explanation that would distract us. Okay, omega is 0.1 now, and that's radians per second. Okay. Now we want to know what happens a millisecond later. Well, one thing we can see is if we multiply radians per second by seconds, we're going to get radians, right? Okay, so in terms of the units, it would make a certain amount of sense to multiply this by a time or a time interval. Maybe even multiply this by a millisecond. That might tell us something. Well, let's think. Now, really, we need to find new values of omega and theta after 1 ms millisecond. And that's the same as 0.001 second. What are we going to do with that? To find the new values of omega and theta, we need to find the changes in omega and theta. Okay? i.e., find delta omega and delta theta. Okay, what do we have here that allows us to find delta omega and delta theta? Where do we see delta omega? Well, we see it here, but we didn't see it in the original statement of the problem, did we? In the original statement of the problem, we were implicitly told what delta omega and delta theta are. If we didn't take the time or didn't go through the step of writing out what it means for omega to be the rate of change of theta with respect to t, or the same type of statement for alpha, we wouldn't find delta omega anywhere. Now, once we develop a deeper intuition for this, we kind of implicitly know it, but right now we need to implicitly state it. As soon as we see that this is a rate of change of something with respect to something else, we write out what that means so that we have the change in that quantity on the paper or on the board someplace. And we don't go into Excel expecting to be able to magically put these into the right place until we've written it out on paper. Later on, when we've done some work with this, when we get to the point where we're adept and have an intuition about it, then we can dive into Excel and we know how to set it up. But we have to work out several problems in paper before we can do that. Of course, several problems have been assigned, but not everybody's been able to do them. Okay. Here's what to do if you encounter a problem of this nature. Again, emphasize, this is why you have to write down the meaning of the rate of change, which means you have to know the definition. Then, when you see that you need to find the new value of omega and theta, you understand that you're going to have to, well, you know omega and theta, all we got to do is find how much they change. How are we going to find out how much they change? If we don't have this down, we're hopeless, but if we have this down, we've got a path. Okay, well, let me come back to this. Again, I'm really emphasizing why you've got to take this step and write this down, okay?